Welcome to the deep dive. Today, we're going to crack open Principia Mathematica
Oh, yeah.
by Alfred North Whitehead and Bertrand Russell.
It's a big one.
You might be thinking, isn't that the book that takes like hundreds of pages to prove 1 + 1 = 2?
That's the one.
Well, yeah, but don't worry. That's why you have us. We're going to break down some of the key ideas of
Absolutely.
Principia Mathematica, and more importantly, explain why they still matter today.
Yeah, think of this deep dive as a guided tour through one of the most ambitious intellectual projects ever undertaken.
Okay?
Principia Mathematica was a monumental attempt to show that all mathematics could be built from the ground up using only the rules of logic.
So it's like they were trying to construct the entire mathematical universe using only the building blocks of pure logic.
Yeah,
That's a pretty bold idea.
it is bold.
But why? What was the point of trying to do that?
Well, the idea that mathematics could be reduced to logic is called logicism,
Okay.
and it had been brewing for centuries. Thinkers like Gottfried Leibniz in the 17th century had toyed with the idea,
Okay.
but it really took off in the late 19th century with Gottlob Frege.
Oh, wow.
But then disaster struck.
Ooh, I love a good intellectual drama. What happened?
Frege discovered a fatal flaw in his own system,
Oh,
a
no.
paradox that threatened to unravel the whole logicist project. That's where Whitehead and Russell stepped in.
Okay.
Principia Mathematica was their attempt to fix the cracks in the foundation and build a solid, paradox-free system of logic that could support the entire weight of mathematics.
So it's like they were called in to do damage control after a major intellectual earthquake.
That's a great way to put it.
Okay.
They saw that Frege's system, while brilliant, needed some serious reinforcement,
Yeah?
and their solution was a complex, multi-layered system that we're going to unpack today.
Sounds intense. So what exactly did they try to do in this massive 3-volume work?
Right.
I mean, where do you even start when you're trying to rebuild mathematics from scratch?
Well, they start at the very beginning.
Okay.
With the most basic elements of logic,
Okay.
things like and, or not what we call propositional logic.
Right.
From there, they build up a system for dealing with statements that involve quantities and objects.
Okay.
What's called quantificational logic.
Okay.
You know, like all cats are mammals, or there exists a prime number greater than 100.
Okay. So it's like they're laying down the rules of the game before they start playing it.
Exactly.
But how do you go from simple logical statements to something as complex as, say, calculus?
That's where it gets really interesting. Principia Mathematica meticulously builds up a system of definitions and proofs,
Okay.
showing how you can derive more and more complex mathematical concepts from these basic logical building blocks.
And all of this with a heavy dose of symbolism, right?
Oh, yeah.
Didn't they basically invent a new language to express their ideas?
They did, and while it might seem like a headache to us today, it was crucial for their project.
Right.
Their system of symbols allowed them to express their ideas with a level of precision and rigor that wasn't possible using ordinary language.
Okay.
Think of it like a highly specialized toolkit for building a skyscraper of logic.
I'm starting to see why this book has a reputation for being dense.
It's dense.
But I have to ask, wasn't it incredibly tedious? I mean, page after page of symbols and proofs. Didn't they ever get bored?
Well, even brilliant minds need a break now and then. In fact, there's a famous anecdote about a particularly long and convoluted proof in Principia Mathematica.
Really?
After pages and pages of dense symbols.
Yeah.
There's a footnote where Russell simply writes, "This proof is tedious."
They needed a little comic relief
They did.
after all that intense logic
A
chopping.
little bit.
But tell me, how do they actually deal with paradoxes, like the one that tripped out Frege? It seems like if you're trying to build a perfect airtight system, one little paradox could bring the whole thing crashing down.
That's exactly the challenge they face.
Yeah.
Remember Russell's paradox?
Oh, yeah.
The one about the barber who shaves all men who don't shave themselves?
Yeah, the one that makes my head spin every time I try to think about it.
Well, to avoid those kinds of self-contradictory loops, Whitehead and Russell introduced a system called the ramified theory of types.
Okay, break that down for me.
Okay.
What in the world is a theory of types?
Imagine a library with different floors for different kinds of books.
Okay.
You wouldn't want a cookbook ending up on the philosophy floor, right? It would just cause confusion.
Yeah, that would make finding the right book a nightmare.
Exactly. The theory of types is kind of like that.
Okay.
It organizes all the objects of logic and mathematics into different levels,
Okay.
or types, to prevent those self-referential paradoxes from popping up.
Okay.
It ensures that you can't have, say, a set that contains itself, because that would be like a book on the wrong floor of the library.
Ah, so it's like a set of rules that keeps everything in its proper place, logically speaking.
Precisely.
Okay.
It was their way of making sure their logical system was well organized and free from those pesky contradictions that could threaten the entire project.
That makes sense. You can't build a solid foundation for mathematics if your logic is riddled with paradoxes.
Right.
But how did this theory of types actually play out in Principia Mathematica?
Well, one way it showed up was in their approach to sets.
Okay.
Instead of treating sets as objects in their own right, they define them in terms of propositional functions.
Okay.
It's like saying, we're not going to talk about sets directly, we're going to talk about the properties that define them.
I'm sensing a but coming.
You're right. This approach, while clever, had its limitations.
Okay.
For instance, it prevented them from having a set of all sets,
Right.
because that would create a self-referential loop.
So their system could handle sets within specific types,
Right.
but not the idea of a set that encompasses everything.
Exactly. They had to come up with some clever workarounds using contextual definitions to eliminate class terms, similar to the theory of definite descriptions.
It sounds like they were constantly walking a tightrope trying to stay true to their logicist principles while avoiding the pitfalls of paradoxes.
Exactly. And that's just one of the many challenges they tackled in their quest to rebuild mathematics from the ground up.
Yeah.
Speaking of building blocks, let's move on to how they define something we usually take for granted, numbers themselves.
Wait, they had to define what a number is?
Yes.
I thought those are just given.
Remember, their goal was to reduce everything to logic,
Right.
right? So even a simple concept like 2 needs to be defined in terms of logical building blocks.
Okay.
And that's where their definition of numbers as classes of similar classes comes in.
Hold on. Classes of similar classes, you're going to have to explain that one.
Okay.
Um,
Imagine you have a bag of apples and a bag of oranges, each containing 2 pieces of fruit.
okay, got it. 2 apples, 2 oranges.
Now, according to Principia Mathematica, 2 isn't about the apples or the oranges themselves.
Right.
It's about the fact that those 2 sets share a common property. They both contain the same number of things.
Okay.
So 2 becomes the class of all pairs,
Okay.
regardless of what those pairs are made of.
Wow. So it's not about the things themselves,
Right.
but about the relationship between sets of things that have the same quantity.
You got it. They define numbers based on the concept of equinumerosity
Okay.
or similarity between classes.
Mind officially blown.
It's wild.
But hold on. If defining 2 took that much work, how long did it take them to get to something like 1 + 1 = 2?
Well, you might be surprised to hear that the proof for 1 + 1 = 2 actually appears relatively late in Principia Mathematica.
Wait, seriously?
Yeah.
That seems backwards.
It does, right? But remember, their focus was on developing a general theory of numbers first.
Okay.
And 1 + 1 = 2 was just one specific application of that broader theory.
Okay.
They had to build the entire foundation before they could put the roof on.
I'm starting to see the logic in their approach, even if it seems a bit counterintuitive.
Yeah.
But I have to ask, did other mathematicians at the time think this was a crazy way to do things?
Well, Principia Mathematica sparked a lot of debate,
I bet.
and certainly wasn't without its critics.
Right.
But it also had a profound influence on the development of logic and mathematics in the 20th century.
Right.
We'll delve into some of those controversies and the lasting legacy of their work later on.
Okay.
For now, let's take a deeper dive into how they tackled a specific set of numbers.
Okay.
The natural numbers.
Sounds good. The natural number, those are just the counting numbers, right? 1, 2, 3, and so on.
That's right.
Okay.
But even something as seemingly simple as the counting numbers required a rigorous and surprisingly complex treatment in Principia Mathematica.
Okay.
Buckle up, we're about to enter the realm of Peano's postulates.
Oh, Peano's postulates. Those sounds familiar.
Yeah.
But I need a refresher.
Well, Peano's postulates are a set of axioms that lay down the basic rules for how natural numbers work.
Okay.
Think of them like the fundamental laws of the counting universe.
Okay.
They tell us things like 0 is a natural number,
Right.
every natural number has a successor, and so on.
Okay, so these postulates are kind of like the rule book for how counting works.
Exactly. And what Whitehead and Russell set out to do was to show that these fundamental rules of arithmetic
Okay.
could be derived from their logical system.
So it's like they were proving that the very act of counting is based on logic.
Yes.
That's pretty mind-blowing. But how do they actually go about doing that?
Well, remember those classes of similar classes we talked about earlier?
Yes.
They used that same framework to define the natural numbers.
Okay.
They started by defining 0 as the class of all empty classes.
The class of all empty classes? That's a bit of a head-scratcher.
It is, right?
Yeah.
But think about it. If you have a bunch of bags and each bag contains nothing,
Yeah.
they all have the same quantity, right? They're all empty.
Okay, I see where they're going with this.
Yeah.
So 0 becomes the representative of all those empty sets.
Exactly. Then they define 1 as the class of all classes that contain a single element,
Okay.
2 as the class of all classes that contain 2 elements, and so on.
So they're building up the natural numbers step by step, defining each one, based on the concept of equinumerosity.
Precisely. And from those definitions, they were able to derive Peano's postulates,
Okay.
showing that those fundamental axioms of arithmetic were actually consequences of their logicism.
That's incredible. Like they're showing that the very act of counting is rooted in logic.
It is amazing.
But I have a feeling this is just the tip of the iceberg.
Oh, yeah.
What other mathematical adventures await us in the world of Principia Mathematica?
Oh, there are plenty more twists and turns to come. In the next part of our deep dive, we'll explore how they tackled even more complex concepts like ordinal numbers, real numbers, and even dipped their toes into the world of measurement.
Okay, get ready for some truly mind-bending ideas. I can't wait to see where we end up next. Welcome back to the deep dive. Last time we journeyed into the heart of Principia Mathematica,
Right.
exploring how Whitehead and Russell set out to build the entire world of mathematics using just the rules of logic.
A big project.
Yeah, we saw how they laid down the groundwork with propositional and quantificational logic,
The basics.
dodged those tricky logical paradoxes with their ramified theory of types,
Yeah, it gets complicated.
and even redefined numbers themselves as classes of similar classes.
Right.
It's like they took apart our intuitive understanding of math and rebuilt it from the ground up piece by logical piece.
It's a pretty amazing feat.
Exactly. But you mentioned last time that things were about to get even more mind-bending.
Oh, yeah.
Something about relation arithmetic. Honestly, the name alone is a little intimidating.
I know, right?
Yeah.
But don't worry, it's not as scary as it sounds.
Okay.
Relation arithmetic is where Principia Mathematica takes a giant leap forward,
Okay.
generalizing the concept of numbers to a whole new level.
Okay.
Remember we talked about how they define cardinal numbers?
Uh-huh.
Those are the numbers we use for counting.
Right.
Well, relation arithmetic allows us to apply similar principles to relationships themselves.
Relationships, like how things are connected to each other.
Right.
I'm not sure I follow.
Okay, so think about a family tree.
Okay.
You have parents and children,
Right.
siblings, cousins, all these different relationships with specific structures.
Yeah.
We can say things like John is the father of Mary or David is the brother of Sarah. Those are relationships that we can represent symbolically.
Okay, I can see that.
Yeah.
But how do you do math with relationships?
That's the ingenious part.
Okay.
Just like we group similar objects into classes,
Uh-huh.
we can group similar relationships into classes as well.
Okay.
For instance, the relationship of fatherhood shares certain properties with motherhood.
Right.
We can call that broader category parent-child.
Okay.
And just like with cardinal numbers, we can define operations like addition and multiplication that apply to these classes of relationship.
Whoa. So instead of just looking at individual relationships,
Right.
we're looking at categories of relationships and doing math with those,
Yeah.
like meta-mathematics.
That's a great way to put it.
Yeah.
And this idea of abstracting away from specific instances to focus on general structures is incredibly powerful.
Right.
It allows us to see connections and patterns that we might otherwise miss.
Okay, I'm starting to grasp the basic idea.
Good.
But can we walk through a concrete example?
Sure. Remember how Whitehead and Russell define cardinal numbers as classes of equinumerous classes?
Yes.
Well, in relation arithmetic, they generalize this to define relation numbers as classes of similar relations.
Similar relations. What makes two relationships similar in this context?
Two relations are considered similar if there's a one-to-one mapping between the elements they relate.
Okay.
It's like saying there's a perfect correspondence between the structures of the two relationships.
So going back to our family tree example, the father of relationship in one family is similar to the father of relationship in another family, even though the specific people are different.
Exactly. The underlying pattern of the relationship is the same, even if the specific individuals involved are different.
This is some seriously abstract stuff. It's like we're zooming out to see the bigger picture.
It is.
The underlying patterns that connect seemingly different things.
You got it.
Yeah.
And Bertrand Russell himself was a huge proponent of relation arithmetic.
Oh, wow.
He even expressed regret later in his life that his contemporaries didn't give it more attention.
Really?
Yeah, he believed it had the potential to unlock new insights in mathematics and logic.
Why do you think relation arithmetic was neglected for so long?
Well, it's a very abstract and complex area of study.
Right?
It requires a shift in thinking, a willingness to step back from the concrete and embrace the power of generalization.
Yeah.
It's not easy, but it can be incredibly rewarding.
I'm starting to see why Russell was so fascinated by it.
Yeah,
It's like a whole new dimension of mathematical thought.
totally.
But I have to ask, how did this idea of relation numbers actually play out in Principia Mathematica? Did they use it to build up other mathematical concepts?
Absolutely. Relation numbers are the foundation for how they tackled ordinal numbers, which are used to represent positions in a sequence first, second, third, and so on.
So ordinal numbers are about order, while cardinal numbers are just about quantity.
Exactly. And just like they define specific cardinal numbers like 0 and 1,
Uh-huh.
they used relation arithmetic to define specific ordinal numbers.
Okay.
For instance, 0 is defined as the class of all relations that relate nothing to anything.
Okay, so it's building on the same logic, just applied to a different type of number?
Precisely.
Okay.
And with this system of ordinal arithmetic, they were able to explore some truly mind-blowing concepts like transfinite ordinals numbers that go beyond the finite and into the realm of infinity.
Wow, we're really getting into the deep end now.
It's getting deep.
But before we dive into the infinite, let's talk about something a bit more down to earth.
Okay.
The real numbers.
All right.
I mean, we all learned about those in school, right? Didn't they have to define those too?
Of course, remember they were trying to build all of mathematics from the ground up.
Right.
And that means even something as familiar as the real numbers, those numbers that include both rational and irrational numbers, had to be defined in terms of their logical system.
Okay, so how did they tackle that challenge? Did they define pi as a class of something?
Well, they didn't define pi directly.
Okay.
Instead, they defined real numbers as the series of segments of the series of ratios,
Okay.
or in more modern terms as Dedekind cuts of the sequence of rational numbers.
Dedekind cuts. I'm not sure I remember what those are.
Imagine you have a number line with all the rational numbers.
Okay.
Those are numbers that can be expressed as fractions.
Right.
Now, a Dedekind cut is a way of dividing that line into two sets,
Okay.
where every number in the first set is less than every number in the second set.
Okay, so it's like slicing the number line in two, but not necessarily at a rational number.
Right.
What does that have to do with real numbers?
Here's the fascinating part.
Okay.
Every Dedekind cut corresponds to a unique real number. If the cut falls on a rational number, that number is the real number represented by the cut.
Okay.
But if the cut falls between rational numbers, it represents an irrational number like pi or the square root of 2.
So they're using these cuts to fill in the gaps between the rational numbers.
Right.
Essentially defining the irrational numbers in the process?
Yes.
That's pretty clever.
It is,
Yeah.
and it's another example of how Principia Mathematica uses a seemingly simple concept, in this case of writing a line, to define something incredibly complex and fundamental to mathematics.
I'm starting to see how their approach, while abstract and complex, is incredibly powerful.
Yeah.
It allows them to build up the entire mathematical universe from a few basic logical building blocks.
Right.
But I'm curious, did other mathematicians at the time think this was the right way to go about things? Or did they have different ideas about the foundations of mathematics?
Principia Mathematica definitely sparked a lot of debate and controversy.
I bet.
And there were alternative approaches being developed at the same time, like Cantor's set theory. But that's a discussion for another time.
Right.
For now, let's shift our focus back to Principia Mathematica.
Okay.
And explore how they played their logicist framework to more concrete areas of mathematics, like measurement.
Okay, measurement sounds a bit less abstract than Dedekind cuts and transcendent ordinals.
Yeah, we're coming back down to earth.
I'm ready to come back down to earth for a bit.
Uh-huh.
What did Whitehead and Russell have to say about measuring things? Welcome back to the deep dive. We're in the final stretch of our exploration of Principia Mathematica, that monumental work where Whitehead and Russell tried to show that all of mathematics could be built from pure logic.
Right, we've come a long way.
We've seen how they tackled everything from basic logic to mind-bending concepts like relation arithmetic and Dedekind cuts.
Yeah, it's been a wild ride.
But last time you hinted that they didn't stop there.
Oh, no.
They even ventured into the world of measurement.
They did.
Now that sounds a bit more down to earth than some of the stuff we've been talking about.
Right, a little more practical.
Did they really have to reinvent the ruler too?
Well, not exactly. They weren't building physical rulers,
Right.
but they did have to define what measurement means within their logical framework.
Okay.
And their approach was, as always, quite fascinating.
Okay. I'm intrigued. How do you define measurement using logic? It seems like those two things are miles apart.
You might think so, but Whitehead and Russell saw a deep connection between the two.
Okay.
They argued that magnitudes like length or weight
Uh-huh.
aren't inherent properties of objects,
Okay.
but represent the relationships between objects.
So instead of saying an object is 5 meters long, they would say it's 5 meters longer than some other reference object.
Precisely. It's a subtle but important distinction.
Okay.
They shifted the focus from intrinsic properties to relational ones.
Right.
Even when it came to something as seemingly straightforward as measuring a table.
It's like they're saying that measurement is always about comparison,
Exactly.
about how things relate to each other.
Exactly, and that fits perfectly with their broader project of reducing everything to logical relationships.
Right.
They even went on to develop a whole theory of measurement that could handle things like angles and points on a curve,
Wow.
things that are a bit trickier to measure than just straight lines.
So they weren't just dealing with the easy stuff.
Nope.
They were really trying to build a comprehensive theory of measurement from the ground up, just like they did with numbers.
Absolutely. Their goal was to show that even something as practical as measurement could be grounded in their logical system.
Now, I remember you mentioned earlier that they originally planned to write a fourth volume of Principia Mathematica
Oh, yeah,
devoted entirely to geometry.
that's right.
Did that ever happen?
Sadly, no.
Oh,
They started working on it, but it never got finished.
that's a shame. I would have loved to see how they tackled the world of shapes and spaces using their logicist approach.
I agree, but even without that fourth volume,
Yeah,
Principia Mathematica stands as a monumental achievement.
right.
It gave us a glimpse into how they might have tackled geometry, grounding it in the logical relationships between points, lines, and planes.
It's amazing to think about how far they were able to push their system.
It really is.
But even with all their brilliant insights and meticulous proof, I imagine their work wasn't without its critics.
You're right. Principia Mathematical sparked a lot of debate and faced criticism from some mathematicians and logicians.
What were some of the main sticking points? Was their whole project just too crazy for most people to accept?
Well, crazy might be a bit strong,
Okay.
but there were definitely some points of contention.
Okay, like what?
One of the most common criticisms was directed at their use of the axiom of reducibility.
Ah, yes, that's the axiom they introduced to deal with some of the complications of their theory of types, right?
Exactly. It allowed them to simplify their system in a way that made it more workable, but some critics saw it as a bit of a cheat.
Hmm.
They argued that it wasn't really a logical principle, but more of an ad hoc assumption smuggled in to make their system work.
So, like, they had to introduce a bit of the workaround to make things fit together.
You could say that, and for some, that raised questions about the whole logicist project.
Yeah.
If you have to introduce axioms that can't be derived from pure logic, then maybe mathematics isn't reducible to logic after all.
That's a pretty fundamental challenge to their whole project. It's like finding a crack in the foundation of the building you just spent years constructing.
Exactly, and that debate about the nature of logic and the foundations of mathematics continues to this day.
Right.
Principia Mathematica didn't settle the issue, but it certainly brought those questions into sharp focus.
It's incredible how this one book, even with its flaws and unfinished ambitions, has had such a lasting impact on our understanding of mathematics.
It really is a remarkable work.
So wrapping up, what do you think is the most important takeaway from Principia Mathematica for someone who isn't a mathematician or a logician? Why should we care about this dense, complex, and sometimes controversial work?
That's a great question. I think the most important takeaway is the sheer audacity of the project itself.
Okay.
Whitehead and Russell set out to show that the entire edifice of mathematics, with all its complexity and beauty,
Yeah.
could be built from the ground up, using only the rules of logic.
Yeah.
Even if they didn't fully succeed, their attempt was a testament to the power of human reason and the enduring quest to understand the world through the lens of logic.
It's like they were trying to map the entire universe of abstract thought, and they came pretty darn close.
Exactly. And that spirit of exploration, of pushing the boundaries of what we think is possible,
Right.
is what makes Principia Mathematica such a compelling and inspiring work, even a century after it was written.
Well, it's been an incredible journey exploring the depths of Principia Mathematica with you.
I've really enjoyed it.
I think I need to go lie down and digest all this mind-blowing information.
Take a break. It's a lot to take down.
Until next time on The Deep Dive, keep exploring, keep questioning, and keep diving into the fascinating world of ideas.